Yeah, so yes, it's really a great pleasure for us to have Professor Paul Hamilton from UCLA to give us this week PAP seminar. Especially in the huge time difference between Singapore and LA. So just remind our audience that time in LA is 10 p.m. So don't fall asleep.
It's a day before, which I almost missed that it was a day before as well.
Yeah, it's very hard to calculate. So Paul did his undergraduate at Harvard, and then he went on to Yale for PhD study, and then he moved to Berkeley, where we have a few years of overlap, and that's where I met Paul. As you can see from Paul's short biography, he has a very broad range of interests in physics. So in particular, he's an expert in using atomic physics techniques with tabletop apparatus to explore exotic physics or testing high energy physics. So he did his PhD work with on EDM experiment with it's a lead monoxide, right?
Mm-hmm.
At Yale, and then at Berkeley he started using atom interferometry to constrain and probe dark matter and dark energy physics. So now he's in LA, and today he will be give us a seminar on what he has been doing at UCLA. Okay, so Paul, please go ahead.
Great, thank you very much for the invitation, Shayu, and thank you for the nice introduction as well. And I hope someday I can actually get to visit you in person and see your wonderful institute as well. I was looking at your website and it seems like you all are doing an amazing amount of different things there. Okay, so can everybody see my screen? I'm going to take that as a yes.
Yes, yes, yes. Perfect.
Okay. Great. And yes, please feel free to ask questions. UCLA in particular, we love asking questions. We usually have 1 million interruptions in our seminars. I know it may not be usual for you guys, but I would love to have questions, so feel free to interrupt me at any time. I tried to keep it rather general because it seems like you are a broad audience in physics. And again, I'll be talking about sensing motion with cold atoms and ions. So to start with, let me give a brief outline. I wanted to give an ultra brief intro to ultra cold atomic physics, AMO, and precision measurements. And I'll talk a little bit about matter wave force sensors. In particular, one thing that I started at Berkeley and an experiment we're developing at UCLA. And then I'm going to end up with a second experiment at UCLA where we're trying to use a single ion to make a gyroscope. So for a lot of you, this is probably obvious, but I know it wasn't for me when I went to physics grad school. So what is AMO physics? Give an ultra brief introduction. So it stands for Atomic, Molecular, and Optical Physics. And if you're not in the field, you might ask, why is it interesting? We knew the structure of atoms and molecules in the 1940s. And yet this field seems to be having a huge resurgence in the last couple of decades. In fact, there's been 5 Nobel Prizes in the last 20 years. And again, I like questions, so why? Why has there been that many? I would argue that one of the leading causes is that we've increasingly have more and more precise ability to control individual quantum states. And how do we do this? Well, there's several ways to do it. I'm going to focus on one method that relies on ultra cold atoms and ions in our case. And that relies on a technique called laser cooling. So this is what allows us to get down to very low temperatures. And here are just some pretty pictures, some from UCLA, showing individual ions, trapped particles trapped in a crystal, in the Eric Hudson lab, Campbell lab as well. Here's another picture showing a cloud of neutral calcium atoms with ions interacting with it. And then these days, there's even molecules that have been laser cooled. So it's a very versatile technique. And in the last 30 years, it's really revolutionized our field. So how is this related to our precise control of quantum states, the cooling aspect? In other words, why is being cold so cool? Well, the main reason is pretty simple: undergraduate physics, the Boltzmann factor. If you think about what is the probability to be in a state, in a quantum state, well, we learned that it depends on the exponential of e to the minus the energy over kT. And if kT is much smaller than the energy of your first excited state in your system, you have a bunch of energies in your quantum system, then you have a very high probability, close to 1, of being in a single quantum state, or the ground state. So this ability, which really came about with laser cooling, has allowed us to prepare and manipulate single quantum states, and that's a powerful new thing that we can do. It provides a couple opportunities. It provides us a means to understand and harness quantum interactions, or quantum-assisted technologies, which I know there's a lot going on at your institute. And it also allows you the ability to precisely test predictions of fundamental physics. And I'll get into that in my talk. So I wanted to give just a simple example. The world we know runs on atomic clocks these days. On the left is a picture of an atomic fountain clock. It's actually looks somewhat similar to an apparatus that Yu built at Berkeley as a postdoc. And it is basically the thing that defines the second for the world. So this is the US version. Countries throughout the world have their own versions of this, and it defines what the second is based on the ticks. Here's the principle. You do laser cooling at the bottom of a cloud of atoms. You throw them up through a microwave cavity, and you detect a certain transition. In particular for the second, it's a cesium transition, a hyperfine transition. A certain number of oscillations of this transition define what the second is. So it's exactly the 9,192,631,770 oscillations is what we define as a second. Again, this is necessary for a lot of things: cell phones, communication, and then GPS satellites all rely on atomic clocks as well. So what is so good about atomic clocks? Well, they've shown an amazing ability to increase their precision. In fact, you could almost say there's Moore's law for precision. In other words, how well can we measure time? You can think about measuring time is also very similar to measuring frequencies. And over the last decades, the precision to which we can measure time or frequencies has increased from these atomic clocks. And you can see all the way down to 10 to the minus 18 now. It seems like in the near future, 10 to the minus 20 and beyond is even feasible. So to give you a sense of how precise of a tool this is, if you had an atomic clock at 10 to the minus 18 precision, it means 1 second lost in 30 billion years if you have a slight error from your 10 to the minus 18 level of precision. This is also the equivalent to the gravitational redshift from GR for moving 1 centimeter. So if you move your clock up by 1 centimeter, you can actually see that. Or you can think about this as the Doppler shift on an optical frequency from continental drift. This is a few centimeters per year Doppler shift. So many technological breakthroughs in AMO have been driven by this push to increase clocks. And the question we've been asking in the field, I think in the last decade or two, is what else can we apply these techniques to beyond just keeping time incredibly precisely? It turns out there's a lot of things. So the way I like to think about this for atomic physicists, this great quote by Maslow: all you have is a hammer, everything looks like a nail. So in other fields, particle physics, you can think about this hammer, if you want to learn things, is colliding things together at high energy to produce new particles. Cosmologists, their hammer is that they can make precise measurements by looking back over billions of years. And AMO, again, with these clocks and these other techniques, our hammer is really our precise frequency measurements, which allows us to look for small energy shifts from new types of interactions. So whatever physics we're interested in, we basically try and convert it into a frequency shift and use these techniques to measure it. So a lot of AMO these days is not focused on studying atoms or molecules or the optics. It's actually using these tools to explore many other types of physics. There's a great review. I have a reference up in the corner there in the Review of Modern Physics, talking about all sorts of new types of physics, meaning new particles, new fields that are being searched for using techniques in AMO. And here I have just an example of two subfields that I'm familiar with: matter interferometry and precision spectroscopy, and what sort of applications you can have to fundamental physics. In particular, I'll be focusing on these searches for anomalous forces, the two green ones, also inertial navigation, measuring accelerations and rotations. Okay, so that's the super brief introduction to AMO. I'm going to move on now to a few applications. So first I wanted to just go back to the work that I did do at Berkeley as an introduction to one example of how this works, and talk about how we used a matter wave force sensor to look for dark energy. So what is dark energy first? Well, from the cosmologist, we know that the standard model is incomplete. In other words, cosmologists can tell us what the contents of the universe is to pretty high precision for them, about 3 decimal places now. And what they tell us is that the normal stuff we know, stars and gas, is actually about 5% of our universe. There's about a quarter that we call dark matter. It's something that seems to clump gravitationally. And then there's another 2/3 or so that we call dark energy, which seems to be driving the accelerated expansion of the universe. So we know this part very well. And in fact, in atomic physics, we spent decades testing this. We've done it to amazing precision. Even some of Shah-Yu's experiments measuring the fine structure constant have tested the standard model to 12, 13 decimal places. And so far, it all seems to agree with the standard model of particle physics. But the real question is, what are these other things? So what is dark energy? What is dark matter? You might also ask, why is the universe matter and not antimatter? And these are all experiments that we can address with techniques in AMO. I'll focus on these two. Let's do the applications for the experiments that I've been looking at. So one example, you might ask, if dark energy is some sort of new quantum field, how could we possibly detect it in the laboratory? So one idea might be, well, I said that dark energy helps to drive the expansion of the universe. Maybe we can just measure the local expansion of the universe. Before I said we could measure the Doppler shift from continental drift. Unfortunately, the local expansion of the universe is incredibly small due to dark energy, so we can't hope to see it. The only way that cosmologists see it is by looking at supernovae that are billions of light years away. But another idea could be, well, if this is some sort of quantum field, typically if you add a new quantum field to your theory, it can lead to new forces between objects. And that's the sort of thing we looked at in our experiments in Berkeley. So how did we do this? Well, we used an atomic fountain as a force sensor. Here's a very cartoony picture of how this works. So on this axis, I have time. This axis, I have height. I have my cloud of atoms here. And what I'm going to do is send in 3 laser pulses. You can think about these laser pulses as making a standing wave, which acts as a grating for your atoms. So the atoms we know in quantum mechanics, they act as waves, so they diffract off this grating. If you do things the right way, you can split your atom waves into 2 paths. And this isn't the cloud splitting in half. This is actually each atom is in a superposition of whether it takes the upper path or the lower path. You can send in a second pulse, diffract it again so that they go back towards each other, and then send in a third pulse and interfere and look at the interference pattern at the output. And the basic idea is, well, if you have some force, you can imagine along the vertical direction here, there's going to be a potential energy difference between these 2 paths. And that potential energy difference means that your quantum waves, your matter waves, are going to build up different phases along the paths. So as that potential difference changes, you can measure a phase shift in the interference pattern on the output of your atom interferometer. There's lots of things you can do with this. So there are groups throughout the world that are thinking about trying to build such precise force sensors with atoms that they can detect gravity waves. At Stanford, they're going to do tests of general relativity with a 10-meter high atomic fountain. And Shah-Yu was involved in this, the fine structure constant measurement at Berkeley, one of the best tests of QED ever. Okay, so one example of a dark energy field that we could consider testing is something called the chameleon field, or the chameleon mechanism. This was proposed by 2 theorists, Justin Curry and Amanda Veltman. And the basic idea is that there's lots of physics that's been tested. If you add a new field into, it's going to mess things up. So if we look at things like the orbits of the planets around the sun, we know them very precisely, and it doesn't seem like there's any extra forces. So if you do add this new field and it's creating a new force, you need some way to hide it. That's where the chameleon comes in. So the idea is that for the chameleon field, around normal matter, it sees a potential that is very tightly curved. In quantum field theory, if the potential for the field has high curvature, that means that it has a high mass, effective mass. It means it's a very short range force between objects. So this chameleon field is mediating a short range force. So the idea is that if you're near a normal thing like a planet or some object in your laboratory, locally, that's very high density compared to the universe, and you get very short range forces, so you wouldn't see them in things like orbits of planets or torsion balances, other sort of macroscopic tests. But out in the universe where the density is extremely low, this curvature goes down, and the field becomes very long range, and then you can see effects like driving the expansion of the universe, for example. So how does this work with atom interferometry? How do we test it? Well, the idea is that we have a vacuum chamber, and with AMO, we're usually operating in ultra-high vacuum, so a very good vacuum inside this vacuum. And then we put a test mass in that's high density, and it creates some sort of gradient in this new electromagnetism, then we could attribute it to a new field. There are other tests, of course, if we did see this, that we'd want to confirm that it really was coming from the chameleon field. We could look at distant dependencies, things like density. There's a couple other things that we could check. But for now, we just want to see if we see this force. Again, the basic idea is that the atoms are going to act as almost perfect test masses for this force. They don't perturb the field themselves because they're so small in mass that they can't create a high local density. So this is what the experiment at Berkeley looked like. It's more just to show you the typical AMO lab, that it's very complicated, many lasers, many things going on for it. But once we had it all up and running, at the end of the day, to summarize it in just a few slides, this is what the experiment looked like. So basically, we would run the experiment in two configurations. We would place our atom interferometer near a test mass. It was sensitive to forces along this vertical direction. So if the chameleon field was there creating new force, we'd expect to see an anomalous acceleration bigger than just gravity. And then we'd run it off to the side where the atoms are not sensitive to any forces from the chameleon field. So that's what these blue and red points are. And you can see they agree quite well. So we don't see much of a difference. We don't see anomalous acceleration. And with atom interferometry, you can place very tight constraints. So we could say that there was not any acceleration at a limit of 45 nanometers per second squared. In other words, this is around 10 to the minus 8, 10 to the minus 9 of normal gravity with 95% confidence. Then you can talk to your theorist friends. In fact, Justin Curry worked with us, the guy that came up with this theory over a decade ago. And you can place limits on parameters in the theory. So it's not too important. These are basically, there's a few free parameters in the theory. This line here is actually what you expect if you want to explain the dark energy density of the universe that's been observed by cosmologists. And the point is these colored areas are regions that we've excluded. So atom interferometry, we've excluded all this blue region. Torsion balances excluded this region here. There's still a little tiny region where it might be possible that chameleons are dark energy, but for the most part, we've gotten pretty close to ruling out this theory. There's other types of theories as well. I won't go into details, but if anybody wants to know, feel free to ask, that we can also place constraints on. Okay, so that was all kind of just a brief intro to the idea of using AMO physics for testing other types of physics and precision measurements. Now I want to get into the work that I've actually been doing at UCLA over the last few years. So the first thing I'm going to talk about is a Bloch force sensor. So the inspiration for this came from working on that previous experiment where you saw it was a fairly complicated experiment. I'd mentioned that you have these atoms that are going on this trajectory. You send laser pulses in to separate them, bring them back together. They're all in free fall while you do that. I had mentioned that. So the fountains, why you get these larger and larger atomic fountains, I mentioned the 10-meter fountain. It's because everything's in free fall. So if you want to make a long measurement, you need to have a huge apparatus to give you enough time to make that measurement since they're falling. This seemed like a pretty big limitation for things like testing forces near a mass. You can imagine that if your atoms are falling by your mass, you're not going to have much time to make your measurement. And in general, the longer you can measure something, the higher the precision, we all know. So I wanted to make something a little bit different. I also wanted to have something that can make continuous measurements. So most of these experiments take a few seconds to load atoms, send these laser pulses, do the whole thing. And you get about 1 measurement a second at the end of the day. So here is my picture of what I'd like as an ideal atom interferometer. I'd want something simple, compact, so I can make short-range measurements close to masses. Still want the high sensitivity. Ideally, I'd like a continuous measurement. The goal is basically, I'd like to just turn on a laser, shine it on these atoms, and detect some signal on a photodiode. And I'd love also to be able to see AC signals. So I'll get into that a little bit, but there's theories out there that predict there could be oscillating forces as well. And when people are integrating over long times, looking for small forces, they would have missed these oscillating forces. So the idea was, well, what if we put this in a cavity and we monitor the effect the atoms have on a standing light wave in a cavity, and we just directly read out that light? How would that work as a force sensor? So here's the basic principle. It gets into some atomic physics for this, so quantum physics, you should say. So we have our standing wave of light in an optical cavity, and now we trap atoms in the standing wave. It's a pretty standard technique in AMO. You can have atoms attracted to regions of high intensity or low intensity, depending on how you detune your laser. This is called an optical lattice. So inside that optical lattice, if this is my z-axis, my wave function is going to kind of be peaked at the point in these standing waves. So every wavelength, or half wavelength in this case, I'll have a peak in my atomic wave function. You can think about this potential that the lattice is creating, the standing wave of light in here. It looks periodic, it has some tilt to it because I have gravity, which is creating a linear potential. And what's going to happen? Well, the idea is that this atomic wave function, and I'll go into detail on how this works, it's going to modulate at something called the Bloch frequency if you apply a force in the z direction. So the wave function is sort of going to wiggle back and forth between this black line and this blue dotted line here. And as that wave function changes, it's going to change how it couples to this lattice, basically the overlap between the atoms and the optical light in the cavity. And that could lead to modulation of the output light of your cavity. So let me remind you what these Bloch oscillations are. You might remember from beginning quantum mechanics. The Bloch theorem basically says that if you have a particle in a periodic potential, you can write down its wave function as 2 parts. One is just another periodic function. So this is something that repeats, in our case, every half wavelength in the optical lattice. And then you get another term here, e to the I QR, that looks like some phase. In fact, if we kind of squint at this, our normal plane wave, we think of e to the I KR, where K is a momentum. In this case, we call this Q a quasi-momentum. So it acts kind of like a momentum, but in a periodic potential. So Bloch had shown way back in 1928, beginning of quantum mechanics, that if you apply a force, the quasi-momentum will actually change in time. Kind of like you expect from classical mechanics. I apply the force, my momentum increases with the force times the time. One crucial thing is that you get this effect, the Bloch oscillations, from Bragg reflection at the edge of the Brillouin zone. So what does that mean? It takes a little more condensed matter physics here. At the bottom, I've drawn what the energy is for the different levels in our periodic potential, going from a free particle all the way over to a deep periodic potential. So on the left, we have a free particle. You can see this looks like just a quadratic. So if I go back and forth, momentum on the left side, energy here, we expect that the energy is p squared over 2m, right? Just the free particle energy. And I folded it over in a funny way that the condensed matter people do. But if I kind of followed this up over to here, this looks like a quadratic curve. And then you can see as you turn on your potential, you start to get gaps here in your energies. There's certain energies that aren't allowed. And then you can recognize as you get to the right, when you have a deep periodic potential, this basically approaches the harmonic oscillator, where you have evenly spaced levels. Okay, so again, if I apply a force to some particle in here, we're going to be in what we call this ground band of some shallow potential here. The quasi-momentum, which this really should be quasi-momentum in the case where it's trapped, causes Q to change. So it goes across the side here. And then when it gets to the edge of this zone, it actually changes in 2 momentum units, 2 h bar k, back to the other side. And you can think of that as just the atom absorbing 2 photons, or basically absorbing and stimulating emission of 2 photons. And each photon has this momentum h bar k. So it goes over, goes back, goes over, goes back. And that's what this Bloch oscillation is. So you can calculate what the frequency is, and it's just the force times the distance it's going to go over, divided by h bar. For atomic physics, this is usually kilohertz scale if we're talking about gravity. And people have seen this for over a decade in AMO. So here are some nice pictures where atoms were trapped in a lattice, a force was applied, and they basically ran the experiment over and over again, where they released the atoms, let them fly a little bit, and measure what their momentum was. So the more momentum they had, the farther down the picture they moved. Then they take a picture of the atoms. And you see this nice periodic behavior where the momentum goes down, Bragg reflection, momentum goes down. One of the great things about this technique is for atomic physics, it has unbelievable coherence time for it, that they've demonstrated Bloch oscillations out to 17 seconds. So a lot of experiments in AMO we're used to doing everything in milliseconds. So having 17 seconds means we can get a very precise measurement if you can follow these Bloch oscillations for that long. Okay, so that's the usual method, and that's been demonstrated before. They did this destructively, right? They loaded the atoms in the lattice, allowed them to Bloch oscillate, let go of them, and then took a picture. And then you have to capture new atoms and do the experiment again. And typically that takes a few seconds each time to gather all your atoms. So instead, what we're going to do at UCLA is just hold them in our optical lattice and just monitor those oscillations using the cavity. We've done numerical simulations of this, and sure enough, we get a signal out of the cavity that's proportional to our Bloch oscillation. So this is what the signal will actually look like over time, units of the Bloch oscillation period. If I just look at the light coming out of the cavity, we see these dips at the Bloch oscillation frequency. And you can put in numbers for this, and if you do typical numbers in the lab that we've seen, 1 million ytterbium atoms, this frequency, these are some of the specs for our cavity. You see that if you integrate for about a second, you can get down to 10 to the minus 7 G uncertainty, which is pretty good. This is as good as the large scale, not the largest fountains, but the fountain that we built at Berkeley that dropped atoms over many centimeters. Okay, so what can we do with this? Well, we project with that sensitivity in 1 day of integration, we can get down to 10 to the minus 9 G. This would completely rule out that chameleon theory I showed before and constrain other theories. These are some of the other theories we could measure. We expect that our method would actually have advantages over the typical fountain method. We have reduced sensitivity to vibrations. The whole apparatus will be quite small. The cavity is only a few centimeters long. And the long coherence time allows us to do precise measurements in a short amount of time. Another thing that would be interesting is to look for not dark energy, but dark matter. There's actually a lot of theories now with the big experiments not detecting heavy dark matter. People are beginning to consider very light dark matter would actually act more like a field. And this field can oscillate at its Compton frequency. And what that in practice means is you could get a time varying force. So I've mentioned that earlier, that our technique, since we continuously monitor this Bloch oscillation frequency, if there was an oscillating force happening on the atoms, we would see it as a sideband on our signal. So we could also place limits on certain models of dark matter. Okay, so what does the experiment actually look like? So here's the end result. We have a Zeeman slower, we capture atoms in this intercombination line of ytterbium. You can actually see the little cloud there sitting between 2 cavity mirrors in our chamber, with about 10 to the 5 atoms loaded into our optical lattice. We've demonstrated coupling to the cavity, so we can show if we tune the light onto the resonance with the cavity that it shifts when we put the atoms in there or without it. I'm going to talk a little bit about a recent proof of principle experiment we did using the cavity to detect motion. Okay, so here's the idea. And this we just put on the archive a few weeks ago, and it's in review at the moment. We have our optical cavity. The red here is indicating our lattice potential in which we trap the atoms. The blue are our atoms. This is grossly exaggerated, of course, because this is half an optical wavelength. Really, this whole scale here is about 5 centimeters, so it's about 10,000, I think that's right, at least thousands of these lattice sites. But we've zoomed in on this. Our atoms are trapped in our optical potential. And using some tricks, we can place a second laser beam into our cavity, this green beam that we call our probe. Okay, and how are we going to detect motion? Well, people have studied for a while something called cavity QED, or quantum electrodynamics, where you can get quantum effects if you tune the light that's in your cavity close to the resonance of one of the transitions in your atom. Just looking, was there something in the chat? Not sure. Okay. Again, feel free to ask questions if anybody has questions. Okay, so the cavity in the atoms you can think of as a system of coupled oscillators. The atom can, okay, sorry, I kept seeing the chat pop up there. The atom has some resonance where it wants to absorb light. The cavity has some resonance where an integer number of wavelengths fits between the mirrors. And you can think about it as you tune these two resonances to each other, they're going to be coupled. In other words, the simplest version of this you can imagine is having a single atom in a cavity. You excite it, and when it spontaneously emits, if it emits into the cavity, the photon will bounce back and forth the cavity, and it could be reabsorbed by the atom. So the photon can kind of slosh back and forth between either the atoms being excited or the cavity. From pretty basic physics, and this doesn't even have to be quantum, but if we have coupled oscillators, you can calculate what happens to their resonance frequencies. People had seen this even a long time ago with pendulums, and if you couple pendulums together, you can get interactions between them. But this formula here is basically showing us what the shift is between our resonance frequencies. So the omega plus and minus are the resonance frequencies for the cavity when it wants to allow light into it, and for the atom when it wants to absorb the light. The delta CA is the difference between those resonances, what the atomic resonance is and the cavity resonance. And then omega here is the coupling term. In other words, how easily the light can go back and forth between the atoms in the cavity. In cavity QED, you can show this is equal to 2 times G, which is this Rabi frequency, single photon Rabi frequency, times the square root of the number of atoms. And this I is something that tells us about the coupling between the atoms in the cavity. So this whole thing in cavity QED is called the collective vacuum Rabi frequency. So we can look at some limits of this. For example, if we say there's no coupling, then the frequencies that you're going to get out are the detuning. So it's going to tell you it's on the atomic resonance for one of them and 0 for the other, which is by definition the cavity resonance. And then we can also look at limits, for example, where we place the atom in the cavity directly on resonance for each other. So the cavity resonance is right on an atomic resonance. So if this is 0, you can see that the splitting in the frequencies becomes plus or minus omega over 2. This is called the vacuum Rabi frequency. It was a pretty famous result about 20 years ago where you place an atom in a cavity and you can see that the mode, the transmission spectrum gets split. So anyway, for us, what we care about is that this omega is the coupling between the atoms in the cavity. And what we're going to use is this I depends on the overlap of the atoms in the cavity mode. So in other words, how much are the atoms sitting on the maximum parts of the probe mode in our case. So if the atoms are all sitting where there's no probe light, you can imagine the probe light is not going to be sensitive to them. It's sitting where there's a lot of probe light and there's going to be a strong coupling. Okay, and then if we take this formula in the far detune limit, in other words, we go off resonance, off the atomic resonance, and we look at what the shift is on one of these. This is the atomic resonance. Sorry, this is the cavity resonance. It looks like our coupling term, our Rabi frequency squared over detuning. So this looks very much like a normal AC start shift for the AMO people. This is actually the shift of the cavity resonance, not the atomic resonance. So how do we use this to detect motion? Well, what we're going to do is we're going to look at the expansion of the atoms as we release them from an optical lattice. So on the left, I have some snapshots showing we start the experiment at 0 microseconds. we've loaded the atoms into an optical lattice. So they have these peaks every half a wavelength, the blue. Our probe is sitting there, and we're sitting at the minimum of the probe initially. Now we turn off the optical lattice, we leave the probe on, and the atoms begin to expand. The probe is very low intensity, so it can't trap the atoms. So they basically freely expand at this point. And if they're at some finite temperature, then they start to expand outwards. And after just microseconds, they're moving some fraction of an optical wavelength. You can see at 4 microseconds, you've got an almost uniform density over the optical wavelength scale. So why does this matter? Well, you can see that the overlap between my atomic wave function and this probe is going to change very quickly for it. So if we just scanned what the transmission of the cavity was at these different times, initially we'd see a cavity resonance at some value at 0 microseconds. And then as the atoms expand, that cavity resonance is going to move. Now you can imagine if you just sit at 1D tuning, you shine your laser at your cavity, and you look at the transmission. For example, if we choose right here, initially I'm going to have low transmission at 0 microseconds. As the cavity resonance shifts across, it goes high, and then it keeps going and it goes back to low again. And sure enough, we did this experiment. We load the atoms into the cavity, release it, look at our probe transmission, and we can see just that we get a peak of transmission, then it drops back down. The speed through which this goes through the resonance or the cavity shifts is going to depend on how quickly these atoms expand, which depends on their initial temperature. So we monitor the cavity transmission at some fixed detuning. That's what the theory looks like. That's what the data looks like. And then to check that we know what we're doing, we compare it with just a traditional method. This method is usually used in these experiments where I have my cloud of atoms. I just look at their overall expansion, basically take snapshots. I do one experiment, wait a few milliseconds, take a snapshot, do another experiment, wait a few more milliseconds, and see how quickly the whole cloud expands over kind of millimeter scales. That's typically how you'd make the measurements of temperatures. And you can see these temperatures are really small. So the time of flight fit temperature, we're talking microkelvin temperatures for this. And then this is, on this axis, our new method using the transmission through our cavity. And you can see that it agrees qualitatively quite well. The blue and the red are actually the expansion along the cavity axis and perpendicular to it. And in summary, what does this mean? Well, it means that in microseconds, we can detect nanometer scale changes in our atomic distribution. And this is the same method that will be used to detect wave function changes during Bloch oscillations. So I mentioned at the beginning that the Bloch oscillations cause the atomic wave function to kind of breathe in and out. We'll see the same sort of change in our cavity transmission from that. Okay. So with that, I'll move on to the last thing. I think I have about 10 minutes, it looks like. So this is a completely different experiment at UCLA. And the basic idea here is instead of measuring motion or accelerations or forces, another thing that we can do is measure rotations using quantum systems. How are we going to do this? Well, we're going to use a single ion to do this. We're borrowing a lot of techniques from quantum computation or quantum information. So how does this work? So ions are charged and we can make a trap for it. That's a very deep harmonic potential. These traps can be tens of thousands of Kelvin deep. So in neutral atoms, when we're using lasers to trap things, usually they're millikelvin deep. So you can really hold on to charged particles quite well just using radio frequency fields. So anyway, our ion's sitting at the bottom of this deep well here. It's supposed to be that blue blob. And we prepare this ion that we consider a qubit in a superposition state at the center of our trap. So it's in a superposition. This is one ion, superposition of two states. Now, just applying some voltages to our trap, we can displace it. So the ion's sitting out on the edge of the trap. And then we can apply something we call state-dependent kicks. And these are the same kicks I talked about before, where we can take lasers, effectively create standing waves to diffract the atom. In this case, the direction that the atom gets kicked actually depends on the state. So what does that mean? Well, it means if we're in the superposition we get a superposition of the atom going one way and the other in the trap. And it's going to oscillate around and orbit the center of the trap. So we can allow this to happen for a long time. And then if the whole apparatus rotates, there's something called the Sagnac effect, where going around one direction, you have to catch up a little bit farther with rotation. The other direction, you don't have to go quite as far. This is a pretty hand-wavy explanation. But at the end of the day, you get a phase shift because of a rotation. So you can undo all the kicks you did to the ion, and then you can basically read out that phase on your qubit. So if you put in typical parameters, so 100 state-dependent kicks have been demonstrated in ion trappers. If you do 100 micron displacement of your trap using a single barium ion, you find that you have a pretty high sensitivity, about 10 to the minus 6 radian per second in a single second of measurement. This is about what commercial fiber gyros reach right now. So what advantages do we have over traditional methods for this? Well, one thing is that our potential, because it's so deep, it's very harmonic. There are other groups that are trying to do this, for example, with BECs. It's difficult to make clean potentials using lasers, for example. Ions have extremely long coherence times. Things up to minutes have been demonstrated for qubit states. Our rotational sensitivity only depends on how many kicks we give it, the momentum transfer, which only depends on our laser frequency or displacement. In addition, there's some technical advantages. We don't have to cool to the ground state, and we think we can do this with very high bandwidth and dynamic range. So how do these state-dependent kicks work? Well, here are two states. And what we do is we drive a Raman transition between our two spin states, so down and up. And the idea is if we take two lasers with the right polarizations for this, and we're in the superposition state, well, if I start here, and I drive a Raman transition, first I absorb here, and then I stimulate there. So I get a kick in one direction. If I start in my other state, first I absorb the pi photon, I stimulate the sigma photon, I get a kick in the opposite direction. So in both cases, we get a difference of two momentum kicks from the photons, h bar k. One of the tricks we're using is that we're actually using a pulse laser, a mode lock laser, which has 15 picosecond short pulses. This means that we can get gigawatts per centimeter squared intensity, which is huge. And the pulse laser also repeats at a rate of 80 megahertz. So we get 15 picoseconds at 80 megahertz. And we think that we can actually do a kick in a single pulse, which means we can get these 2 h bar k kicks at 80 megahertz. If you calculate what acceleration this is on your ion, it's about 10,000 g, so 10,000 times the acceleration due to gravity. This is good because you always want to have as much momentum transfer, basically separate out your wave packets as far as possible to get high sensitivity. Okay, and I think in the interest of time, I'll skip through some of this. So this is what the apparatus looks like. We have RF rods that we use to trap the ions. You apply RF to it. You can see a cloud of ions here. Here's a crystal, single ion for that. This is a pretty large trap that we did for our proof of principle. We've demonstrated qubit manipulation, just flopping back and forth between the two spin states using a laser for it. We've also done something called Ramsey interferometry using 2 pulses. And before the quarantine started in the US, we just gotten to the point where we cranked up the intensity of our mode lock laser. This was a pretty monstrous laser. It's 30 watts at this high rep rate. And we could see Rabi flopping where in a single pulse, we could see that the spin state flipped. So over here, I'm showing the probability to be up or down. Basically, in a single pulse, we're getting a spin flip. This means that we have a single pulse Rabi frequency of 30 gigahertz, which as far as we know, it's probably the fastest qubit manipulation that's been done in an ion trap. Okay, so at that point, this experiment started about 2 years ago. We had done the trapping, state preparation, readout. We've done the internal manipulation, basically doing the spin flips. And now we wanted to get to the part where we're actually kicking the ion with this laser. So we're about to work on that. Fortunately, then the quarantine started and we couldn't do experiments. So we've put on our theorist hats. We've just looked at some of our old data and figured out what sort of simulations could we look at. I think I'll go through this, maybe skip over this part. But one thing that we saw that was interesting was that even with a single beam, we could actually drive motion perpendicular to our laser beam, which we didn't expect. Usually when we do these kicks with the laser beam, we expect only to couple to motion along the laser beam. It turned out that this was because we have a focused laser beam, that you have some spatial profile to your laser, and that gradient across your ion can actually be used to drive motion perpendicular to it. This is interesting for a couple reasons. One is that it hadn't been considered previously as far as we know in the community. There's companies even now that are using ion chains for doing quantum computation. A lot of times they focus laser beams on single ions, trying to manipulate them. And what we showed is that actually you need to worry about these gradients out the wings of your laser beam that you might accidentally talk to the next ion over that you didn't intend to, and drive motion perpendicular to your laser beam. In fact, it seemed like with published data, this might explain a good deal of the infidelities observed in these gates. It could also provide a new method that you can get rid of unwanted transitions as well. But I'm going to skip over that in the interest of time. Okay, so we also did a simulation of what we were hoping to do, which was kick our ion. The first experiment we wanted to do was to apply a spin flip with 50% probability. We call that a pi/2 pulse. This is a phase space diagram, momentum and position here. So we apply a kick. We're in a superposition of 2 momentum now. And then we're going to wait some time. And ideally what we get is we kick one part of our wave function that goes back and forth in our ion trap. When it overlaps again, we see a revival in our contrast, we call it, these fringes that we can look at. So these are simulations. Basic takeaway from this is that if we do these 2 pulses, we'd expect not to see a spin flip except when the ion wave packet overlaps again after it's oscillated in our trap. All simulation, that was great. A couple weeks ago, we finally got back into the lab. We started to do these experiments. We could see the first thing we expected, which was the initial kick. The spin flip probability basically levels out to 1/2. So initially, we start in one spin state here. As the wave packets separate, you start to see that you have 2 separate wave packets, and then it just levels off to where you have a 50% chance of being up or down when they're separated. What we want to see is interference between these wave packets. So we waited longer. If we look here, this was tens of pulses. And these pulses are happening every 12 nanoseconds. And if we wait 2,000 pulses, there was an interesting little blip. And this is literally data from this week. So we zoomed in on this. Is it real? It looks kind of like noise, but we did a few experiments. It was reproducible. Sure enough, this is the revival. So we've seen the fact that we can kick our ion, 1/2 of it goes back and forth in our trap. It overlaps again to about 10 nanometer precision. And then we can see revival in a spin flip when that happens. This allows us to measure our trap frequency. We know now that it's 36.2 kilohertz. It's a pretty high precision. We can do more. We can see multiple orbits and revivals for this. We can do these Ramsey fringes I mentioned. I'm not going to go over the details too much, but basically this is the theory. This is the data we got this week for it. So it's just showing that we can do 1D interferometry at least. So that's where we are with that. We can add another check that we can do 1D interferometry. In the future, what we're hoping to do is add this displacement and then kick so that we're actually orbiting the trap, not just going back and forth in one direction. And then in addition, we're going to, of course, go as far as we can with this test. How far can we displace the trap? How many kicks can we do with our laser beam? You know, what's the ultimate limit of our coherence time, and see how good of a rotation sensor we can make with it. And with that, I'll go to my conclusions. So I hope I've convinced you that AMO physics is a powerful set of tools for testing fundamental physics, as well as building practical quantum sensors. I talked a little bit about how I've worked on atom interferometry for placing constraints on certain dark energy models. In Berkeley at UCLA, we're building a new sensor using neutral atoms in a cavity to measure new anomalous forces from dark matter and dark energy, and an ion to measure rotations as well. We're just starting to get to the point where things are exciting here. We've done proof of principle, again, showing thermal expansion of an ensemble in microseconds. And then just a few days ago, demonstrating 1D ion interferometry as well. I should mention that these techniques where we can make this qubit gate in 15 picoseconds. Could also go towards making ultra-fast quantum computation as well. And with that, I definitely want to thank my group, collaborators. Wes Campbell in particular is another professor here that's been working on the ion project with me. It's been invaluable for that. The graduate students, Chandler worked on the terbium experiment, Randy worked on the ion experiment, and the postdocs, Robert worked on the terbium and Adam worked on the ion experiment. They've been absolutely invaluable and taken almost all the data you've seen in this talk. And with that, I thank you and would love to have some questions.
Yes, I have one question. So Paul, for the temperature measurement with the cavity, does the expansion in the transverse direction affect your result, or how do you need to calibrate it, or?
Let's see, I don't know if I put a slide in there with that, but basically, we measure quickly over an optical wavelength the expansion along the cavity direction, and that takes microseconds for that. And if you look in the paper, what you'll see is that you see this transmission change over microseconds, and then you'll see an additional change over milliseconds, and that's as so you have our optical lattice, the atoms expand over optical wavelength. They're also expanding out, which is what Shai is asking. That depends on the size of the laser beam. For us, that's millimeter size. So it's on the order of 1,000 times larger. So in milliseconds, we see a second peak from that. So we can actually measure both the transverse and along the axis, the axial temperatures. And that's what these two sets of data points are.
I see.
For the axial measurement, the transverse, the expansion out of the cavity is absolutely negligible, right? In microseconds, it hasn't moved at all compared to the size of the laser beam.
I see.
I have two questions. One is a kind of like probably a bit fun question. Sorry. One is a kind of fun question that regarding the experiment that you did where you suspended an atom near like a spherical aluminum cavity, and there, like probably you know the answer. That do you know what happens when the atom goes like starts at like a little bit above the sphere, goes you poke a hole, so it goes through the hole, and then it comes out. So like when you showed it to me, it looked like the book of Jules Verne, like a journey through the center of the earth. So what happens when it goes through the center of it? Because for it, it's like the whole earth. So do you expect anything quantitatively different, that the gravitational potential due to the aluminum sphere will affect it when you go through for it, it's like zero and all that?
Sure. Yeah, so that experiment, part of the motivation for the stuff at UCLA is we wanted to be able to just hold the atoms near the sphere for a long time. So the Berkeley experiment, we were basically limited by, we could only, let me stop my share so I can do the bigger picture of myself, maybe. We kept the atoms outside of the sphere and only allowed them to drop a few millimeters, and that was limited our precision for that. If we let them fall completely through, you can imagine if it was completely symmetric, and it started here and went all the way through to the other side,
right?
Basically, the potential would shift sign and we'd see zero effect for it.
I see.
So we always wanted to be at the point where we had the largest gradient. There's also some complications that the chameleon field does weird things inside. And we had theorists model exactly what the field would do near a real source mass.
I see, thank you. I have another question regarding the temperature measurement. There you create a wave, they were like at each independent site, you have this localized wave packet, and then you just let that delocalize due to the temperature. And there the temperature was as high as like 50, 70 microkelvin. So how much was the trap depth that you were staying in the same band, like in the lowest band, so there was no band-to-band transition? And how was the effective mass at that scale?
Yeah, that's a great question. So we, for this experiment, typically, I think our trap depths were something like 150 to 200 microkelvin, somewhere around there. So these atoms are quite hot for that. So they're in many bands. It's almost classical. In fact, we simulated both quantum and classical, and there's not much difference between the two for it. So we're not in the ground band for that. For the Bloch oscillation experiment, that's the next step that we're working towards now, which is cooling to the ground band and then doing the same sort of experiment.
Okay, thank you.
For the Bloch oscillation experiment, yeah, there's an interplay where you need to be at a few recoil energies depth to prevent tunneling to other bands.
Yeah.
But enough that you're holding on to them as well.
Yeah. Okay, thanks. And thanks for the great talk.
Thank you.
Okay, I have also some questions. So thank you very much for this very nice talk, and it's very great, very clear. So regarding also this experiment, I mean, so you have a cavity in vacuum, and this cavity is doubly resonant, right? With one with the lattice field and the other one with the probe field. How do you, in practical, how do you do to have those fields locally, where are the atoms, in opposite of phase, like it's shown in this picture? Yes, in practical, how you do that? And the second question related to this slide also is, how is the quality factor of the cavity? I guess you need a very high quality factor, and so is it? So what is your quality factor, and is it enough somehow, or you want to improve it?
Yeah, great questions. So the quality factor isn't too much for us. It's around 1,000. It means that we have a line width of around 1 megahertz. So yeah, it's decent, but there's certainly cavities that are 100 times better than that. We don't want to have too high of a quality factor because the dynamics change with the Bloch oscillations if your cavity line width starts to approach the Bloch oscillation frequency. Luckily for us, this coupling scales with the number of atoms. So we aren't as concerned as a lot of the cavity QED people are, where they're trying to get to a strong coupling with a single atom. We just want strong coupling or an effect on our cavity with our ensemble. The first question about the phase for that. So we just use 2 different longitudinal modes of the cavity. So the next free spectral range, which is for us a few gigahertz away. If you think about that, that adds 1 more wavelength into the cavity, which means at the center you're shifted by half a wavelength. There's a little bit of a technical trick there that we're using a narrow line on ytterbium. So changing the frequency by a few gigahertz is very far detuned from that resonance, which allows us to have this probe that doesn't affect the atomic transition very much.
Right, I see. So you're on the intercombination line, right?
Yep.
Okay.
Yeah, so not the clock transition, but the
okay.
triple P1, which is a few hundred kilohertz line width.
Yes, okay. Regarding the second part of your talk, I mean, for the gyroscope, I was wondering, I mean, how do you deal with systematic effect here? That sounds a bit, something important in this kind of setup. I am right?
For the ion?
Yes, for the ion rotating. And so
yeah,
you mentioned that the harmony trap should be, I mean, not perfect, but very, very good. I mean, yep. So I guess it's a very challenging aspect here.
Yeah, so you'd be worried about, particularly since we aren't planning on going to the ground state for these ion, or this ion. You wouldn't want something where, for example, the trap frequency changes with the amplitude of your oscillation. In other words, if it's anharmonic, that would be a problem. But even with laser cooling, or ions are millikelvin temperatures in a 10,000 Kelvin deep trap, so it's very, very harmonic for that. And then my postdoc Adam West has a paper out where he considered a lot of different things. So he looked at, we actually want a 2D trap where the trap frequencies are matched, so we get circular orbits. He considered how much it matters matching those 2 trap frequencies, which we can do with voltages on our electrodes. What happens with anharmonicity. Also, if we don't couple the laser along the right direction, if we don't kick straight along the trap axis, what happens? And all of these things, they do have some effect. We have it on the phase and the contrast and the area. But in terms of this 10 to the -6 radians per second type of sensitivity, none of those come at that level. So as far as we know, we should be okay.
Okay, thank you.
Mm-hmm.
So do we have other questions?
Yeah, following this question, so does ion has to be in ground state or?
No, so one of the things I didn't mention or emphasize is that we're using these picosecond pulses. So it's basically an impulsive kick, that the time the kick happens is very short compared to the trap period for it. So you can think about, for example, if I had a coherent state, even if it's excited, I can kick that coherent state just like I would classically, and it works fine. So we don't need to be in a ground state to do that. There's some limit, if you're at a very high thermal state, you start to lose contrast. But for us, I think it was a few % effect.
Well, I think there's a question in the chat. Maybe you want to take a look.
Sure.
Yes, that's right. Do you have access to the chat?
Yep.
Okay.
Okay, so asking, how many Bloch oscillations do you expect to measure before photon recoil from the intercavity probe causes sufficient heating in the axial direction to significantly affect the atomic motion? How does this scale with the probe detuning from atomic resonance and cavity detuning from atomic resonance? Short answer is, in those numerical simulations, we basically choose those detunings to give us many seconds coherence time before we expect any scattering from the probe for it. So it's certainly a concern. We could go near resonance, get a larger effect, but have a shorter coherence time. So there's some trade-off there.
Okay. So here you can do also a non-destructive measurement, right? To some extent in this scheme.
That's right. So there is a theory paper talking about going through the quantum mechanical version and thinking about, back action doesn't seem to be a problem in the regime we're talking about for it. But they had to make some approximations that if you look at the theory, it's pretty difficult because you have this potential that's changing in time as it couples to the atoms, which are also changing in time. So doing an exact quantum calculation hasn't been done as far as I know for it, but at least using reasonable approximations, it seems like it shouldn't be a limitation.
Okay. So if there is no more questions in the chat or directly to the speaker, so maybe thank you very much, Paul, for this very, very nice talks. Enjoy your evening and your night. There is another question. Yes.
Yes. Oh, you cannot see me. Okay.
We cannot see you, but we can hear you. Yes.
Oh, it's okay.
Oh.
Just mute me. Okay. Hello. Can you hear me?
Mm-hmm.
Okay. My question is about the ion experiment. Do you expect a B field, magnetic field, to be a systematic effect? Because if the one spin up is going one direction, spin down is going the other direction, I'm not sure whether you can accumulate different A dot DL phase.
Yeah, that's a great question. So there's some technical things there. We chose 2 Zeeman states for this because it allows us to do these kicks repetitively. That we hope we can, do this kick at the rep rate of the laser. You could also do this with hyperfine states, which is what the Chris Monroe group has done, where they're using m=0 states that aren't magnetic field sensitive. For our experiment, basically a magnetic field is indistinguishable from a rotation. So at least as a sensor, there's a way, there's 2 things we can do. One thing is we can use an applied magnetic field to basically keep us at the most sensitive part of our fringe when we do a rotation measurement. The second thing that you can do is you can actually choose the size of your orbit, so how you displace and kick, such that you get another magnetic moment because you have a charged particle going around in a circle. And you could actually cancel the magnetic moment from your spin with the magnetic moment from the orbit so that you're not sensitive to magnetic fields.
Okay, thank you.
Mm-hmm.
Okay, so if there is no more questions, so again, thank you very much, and have a nice evening and have a nice night in LA, and like weekend as well. You have to wait another day, actually.
I will go to sleep.
Okay.
Thank you for the invitation. I enjoyed it.
Okay, thanks, Paul.
Yep.
Thank you. Goodbye.
Bye.
Thank you.
Bye-bye.